All right, so this next part of the practice test is question number 2, and this one happens at non-standard conditions. And during the pandemic year, when this is being recorded, non-standard condition EMF questions were not tested. And so you can look at the answer in the practice test, but it is not tested on this one. Question number 3, consider the reaction between hydrogen and oxygen to make water. Which element is oxidized? So you have to go through and assign oxidation numbers. So it's 0 here, 0 here, hydrogen's positive 1, oxygen's negative 2. And if you can see, a hydrogen goes from 0 to positive 1, so it goes up in charge, and therefore it is oxidized. So the oxidized species in the reaction is H2. Which element is reduced? You can see oxygen goes from 0 to negative 2, so it goes down in charge, and therefore it is reduced. And so oxygen right here is the thing that's reduced or goes down in charge. How many moles of electrons are transferred in the reaction is written. So now you have to unwrite the balanced reaction into its half reactions. And I'm going to take a little time to do that. And we're going to take the up oxidized part, 2H2, and we're going to write that as going to 2H2O like this. And then if you remember the steps from balancing redox reactions, there's going to have to be a part in there that's used to help balance that, because you're supposed to balance everything except hydrogen and oxygen. Then O is with H2O. So I'm actually going to have to add 2H2O to this side to help balance it. And then balance the H's with H+. And so now since I have 8 hydrogens here and only 4 right here, I need 4 H pluses on this side. Okay? And then after I've done the H pluses, then I use electrons to balance that. And so since I have a 0 right here, I need 4 electrons on this side to make sure that it's 0 on this side as well. Okay, and then I know that I'm going to end up getting these things canceled here as well, but remember it's asking how many moles of electrons are transferred, so that's the key piece right here. Now let's use the other half reaction and let's see if we get the same thing. And that's O2 going to H2O, and I know that there's a 2 in front of the H2O over here, so I'll leave that there for right now. And then I need to balance the oxygens first, and those are balanced. And then I need to balance the hydrogens with H+, and so I'll need 4 H pluses over here to balance that, since there's 4 on this side. Now I can balance the electrons, and as you can see, I'll need 4 electrons here to get it to be 0. And so you can see the 4 electrons are transferred from one side to the other, and so 4 is the answer right here for the reaction as written. And the reaction as written just means that there's a 2 here in front of the H2, there's a 2 here in front of the H2O, so when I took it apart and wrote the half reactions, that's why I left those coefficients in there, rather than use like a half or something else to try to balance it. All right, and in letter D it says, the standard reduction potential is 1.23 volts. Use this to calculate G and K for the reaction and express the units with the kilojoules or joules. And so using your E sheet right here on the back side, it's got the red cat and it's got the equations for how to do these calculations. And we can see that delta G is equal to negative NFE. And then the K, of course, comes from the G is equal to negative RTLN of K, which we'll get to after we do this one first, because we've got to find G first. And so N is the number of moles of electrons that are transferred, which are 4 moles. F is the Faraday constant, which is 96,485 coulombs per mole. And so my moles will end up canceling with my moles right there. And then my E is my voltage, which is 1.23 volts. And volt is a joule per coulomb. And so my coulombs will end up canceling with my coulombs, and I'll end up with my answer in joules. And so multiplying those together, 4 times the 96,000 times the 1.23, my answer in joules would be negative 474706 joules. Be careful to make sure that you put it in joules, or put your units in there and not confuse it and say, oh, it should be in kilojoules, because that's what we usually put G in. But in this case, it's easier to just get the answer in regular joules. Okay, now there's a couple of ways to find K. one way is to say that K is equal to negative RT ln of K. Whoops, I'm sorry, this should have been a G, my bad. G circle right here. And if you solve for K, you have to undo the natural logarithm, and then K is equal to E, because that's what natural log is base E, negative delta G divided by RT. So that's one way you can solve it directly, is with this equation, or you can plug the numbers into this equation and then solve for it. I'll use this equation since it's set up already for K. Let's see. E right here, and then delta G is negative 474706, and that's in joules. And then my R has to be 8.31 joules per mole times Kelvin, making sure that this is in joules and this is in joules, so they cancel. And then T is my Kelvin temperature, and we're at standard conditions, so we're at 298 K. So that makes my kelvins cancel with my kelvins. Well, it ends up that this is the exponent, so these are going to all cancel with each other as well. And then don't forget that there's a negative sign right here in front of it as well, so a negative to a negative. So K is going to end up being a very large positive number, and I think it ends up being on the order of 1.78 times 10 to the 83rd power, which is very common for spontaneous redox reactions, and we can see that it's very spontaneous because G is very negative, and then we see it's got a giant K, which means that the reaction is very far to the right. The products are very favored in this reaction, and there would be many, many of them compared to the reactants. All right.